Okay, if you can hear me, you are live on Facebook and recording, so you are good to go when you're ready.
All right, thank you, Christine. Courtney, would you be so good as to maybe close the doors to the gallery? Thank you. Well, welcome everybody. My name is Michelle Crepeau, and I'm the conservator for the North Carolina Maritime Museum. I'm the artifact doctor on staff. My job is to help take care of the artifacts that we have here in the collection and make sure that they have long, happy lives so we get to enjoy them for years to come. This includes things like trying to physically and chemically stabilize them, clean them, make them look nice, document them, etc. And today we're going to be talking about one of my favorite types of artifacts, or one of the coolest ways that we find artifacts. We're going to be talking about concretion. So many of the artifacts that you'll see here on display that have come from marine archaeological context, so things that have been recovered from the ocean or from a shipwreck, will often be covered in this very dense concrete-like material known as concretions. So this talk will cover a little bit about what they are, and how we as conservators deal with them, how we investigate them to see what's inside, and how we ultimately recover those artifacts from inside these concretions. So to get started, what is a concretion? In a geological sense, a concretion is an aggregate that is made of minerals. A mineral is an inorganic compound. Inorganic in this context is defined as anything that is not carbon-based. So we think of inorganic versus organic as something alive or was living versus something that is not alive. But in chemistry terms, inorganic tends to mean something that is not carbon-based. So it is a non-carbon-based compound. And all minerals will have a unique signature. They'll have a unique chemical or elemental makeup, as well as a very unique sort of geometry, or what we call a crystal structure. So they'll have a very unique shaped kind of building block, essentially, that's a crystal of some kind. And minerals together make up rocks, very simply put. Oops, that was the wrong direction. All right, so there's different types of concretions that we find, just naturally occurring concretions that have no artifacts associated with whatsoever. Because how you get a concretion is that it's a mineral aggregate that forms around something. There's something at the core of that concretion, or was something at the core of that concretion. And this can be very simply a rock, or it can be another mineral deposit, or another layer of sediments. This one right here is known as an ironstone because it has basically iron ore as sort of a naturally occurring core that all this other material has aggregated around. And we'll get into the mechanics of that in a little while. But besides that, we also have concretions that form around formerly living things. That's one way that we get fossils. Sometimes they fossilize inside these concretions. Other times they decay and we end up with these voids in the shape of a living thing like a leaf or a seashell that once was there. And we also have examples of concretions that form around void spaces as well. One of the most well-known ones are geodes. Geodes actually count as concretions. As you can see, there's a hollow center in this very intricate crystalline mineral pattern that is formed around it. So technically a geode is a type of concretion that is formed around an empty space, like an air pocket. Or maybe there was something once at the center that has since dissolved or decayed and deteriorated and is no longer there, leaving this empty void. And of course, the ones we're interested in are the concretions that form around artifacts. So the things that form around man-made objects that end up in saltwater environments. So how concretions form, there are 3 steps. There's precipitation of minerals, there is nucleation of those minerals, and then there's cementation of those minerals. So how they work is that precipitation goes like this. You have a bunch of dissolved material in a solution. So in water, for instance, these materials are called ions, meaning they have a charge. So they are a charged particle, be they a molecule or an atom. These materials are attracted to each other and will form bonds. And when that water is removed, or basically they get large enough, essentially, they will do something called precipitate out of solution. So basically these little tiny pieces, these building blocks will bond together and form a mineral, which will then come out of solution. This will then find something that will act as a nucleus or a center. So this can be anything, again, from an artifact to another mineral to a rock that will then what we call nucleate around it. So essentially it will basically be attracted to whatever the center point is and sort of cluster around it. And then this material will essentially stick together. So cementation is essentially this mineral acts as a natural glue and will essentially stick together both themselves as well as anything else in the nearby environment, including sand, sediment, other types of minerals, sea life, and other artifacts. In the case of the types of concretions we are interested in, it is our artifacts which make up the center of our nucleus. So these artifacts are almost like a seed that around them have grown this sort of mineral base aggregate or cluster around them that is formed first by a mineral product, often which comes from the artifact itself. For instance, if you have an iron object which is in the ocean, that iron will corrode. That corrosion product, as we'll get into in a few minutes, is a mineral. And that mineral will basically act as a glue that will stick to sand and sediment and other things around it, forming this mass around the artifact that is then buried inside of. All right, so kind of also thinking about where these minerals coming from. So there are minerals that can come from the burial environment, so the environment surrounding the artifact. And then as I just spoke about, there's also minerals that are produced by the artifact itself, by its own decay processes. So we can have dissolved minerals that are just dissolved in the water. You can have very hard water, as we're very familiar with here in Beaufort, where you have a lot of dissolved mineral content in your water. So when the water evaporates, you're left with this nice, lovely lime scale on a lot of your sinks. That is an example of having minerals in your water itself. You can also have minerals that are coming into your water from outside sources. There's minerals in the sediments of the ocean bottom. There's minerals being washed in from our rivers and estuaries, from the mountains and from further inland that are providing all this mineral content. And you also have sea life. A lot of our sea life, especially our mollusks, are encased in minerals. Their shells are made of calcium, for example, and a lot of times these produce, and when these start deteriorating and dissolving in the ocean, these also provide a source of minerals, which we'll also get into in a little while. And of course, there's also microbes. We don't think about this one as much, but a lot of microbes, so a lot of bacteria, for example, that can live in the ocean also produces mineral content as a byproduct. One of the kind of most interesting microbes that we're interested in as conservators and as archaeologists are something we call sulfur reducing bacteria, which actually essentially can live in areas where there's no air, because they use sulfur in the environment as their metabolic sort of main source of almost breathing. They basically breathe sulfur, if you would. And as a result, they produce sulfur waste products. And these sulfur waste products can form sulfur-based minerals. It's one of the ways we get pyrite, for example, on our shipwreck sites. And then, of course, there's our artifacts ourselves, especially our metal artifacts. This can include copper alloys. This can include most famously iron material in particular, as well as pretty much any type of metal that is in the ocean will experience some sort of creation of mineral content, depending on how much depends on the thermodynamics of that one type of metal's particular deterioration pathway. We won't get into that in much detail though. So how corrosion of metals makes minerals. So essentially you don't really need to. So all iron, metallic iron is very rare in terms of naturally occurring in nature. We have to make our metal. We have to essentially take raw iron, which is found in a mineral form. We call it iron ore. Some of the most well-known types of iron ore include magnetite, hematite, and goethite, which are iron-containing minerals that we then have to refine into iron ferrite. So basically metallic iron as we know it, that we can work with and make things like nails and shovels and pickaxes and pikes with, etc. Now what happens is that these materials corrode when exposed to certain atmospheric conditions, as this will illustrate. And that corrosion is essentially best thought of as a transformation process, hence our little corrosion fairy. They transform our sort of artificially manufactured iron ferrite back into a mineral form. So they sort of almost reverse that refining process and basically revert our iron back into iron mineral content. This mineral content, then in terms of how the mechanics of corrosion work, you have your, this represents our kind of iron metal ferrite right here, that you can see right here is bonded together. These bonds are created through the sharing of electrons. And when you introduce them to oxygen and water and electrolytes like chlorides, are basically our factors that are charged particles that are near them in solution, essentially they are able to break these bonds by basically forming bonds with them and or stealing their electrons. So those bonds have dissolved, and as a result, our metal ferrite has broken apart into its own metallic cations, or these metal ions that can then do things now that they're dissolved in solution. So this is how we get our mineral dissolved into solution. And if it comes in contact with other materials, it can form new bonds. And then essentially precipitate out as a mineral like goethite over here. And so that was kind of the big takeaway from that, is that corrosion is transformative. It essentially transforms metallic iron into a mineral form of iron that can then be dissolved into metal cations that are in the water, mineral content that can then be used to form your concretion. The takeaway of this slide is that corrosion is also directional. Corrosion essentially is the exchange of ions between one point and another. Galvanic corrosion, which is the type of corrosion that affects metals, which can take place between two dissimilar metals, or even on within the same metal on different sites. There's essentially an anodic site from which material is being taken, electrons are being extracted, and a cathodic site from which electrons are being received and material is being produced, essentially. And just to kind of step back, so when you have a piece of metal that is exposed to certain risk factors, which includes water in all its various forms. Just a reminder, water doesn't just exist as H2O, it also exists in the form of hydroxyl and hydrogen and hydronium ions that are all kind of coexisting at the same time inside your water, that can all essentially be good electron receptors, that can all essentially kind of kick off corrosion. You also have the same thing happening with oxygen air, which is diffusing into your water. And then you also have salt or electrolytes, which basically help conduct electrons through solution. So this all helps move electrons from point A to point B. So the takeaway from this is your electrons are going from your site, which is being corroded and essentially eaten away, to a different site. And at the same time, you also have metal cations, which are being released from this anodic site, being dissolved into your solution, and then producing essentially your mineral content as a result of essentially being minerals floating around the water, forming larger minerals that then precipitate out of solution and form on the surface of your artifact. So as you can see here, this demonstrates you have a site where you have material being taken from, and then a site where you have material being deposited in the form of your corrosion product or your rust. So how this might look in a sort of underwater barrel environment. So we have our iron chain, it's buried in the ocean, it's buried under several layers of sand. The sand is actually wet, there's water in the sand. It's sort of partially almost a mixture in some areas, depending on how boggy it is. So you have access to oxygen and water and electrolytes in the environment. So what you're going to have is corrosion of your artifact. You're going to have the release of these metal iron cations, these basically minerals that are being leaving the artifact, essentially moving directionally into the environment. Well, they'll come in contact with other dissolved minerals, which will then form your corrosion products. You'll have these successive formations of different types of mineral content being layered on top of your artifact, to the point where sometimes you might actually no longer have an artifact. Sometimes you instead might end up with a massive corrosion that has a void inside of it where an artifact used to be, that's in the impression of your artifact, because essentially your artifact has completely mineralized and those minerals have essentially left the building. They have become the surrounding corrosion and eventually the surrounding concretion. So how this then works is you have all this mineral content, all this corrosion product floating around, and you have all these little spaces in your between your sand particles that then are essentially cemented together by the precipitation of these iron minerals out of solution. So you have this kind of glue that is you have this sort of mass that is being held together by this mineral-based glue. And that's how you kind of get your crusty, sandy, salty concretion. As you can see, it's not just corrosion product anymore. It is also made of sand, other types of rocks, other types of sediment that are all stuck together and cemented by this mineral content that has formed as a basis of our iron corroding in the ocean. And sort of add on this, it's not just the iron itself. Concretions are also kind of like miniature reefs. If you kind of think about artificial reefing practices, and the reason that we purposely scuttle ships, for example, or why so many of our shipwreck sites are very diverse in marine life, is because they tend to form natural reefs. And that is because iron in particular, as it corrodes and it's releasing all this mineral content to the water, is very nutritious for a lot of sea life. They are attracted to it. So they will come and basically settle on top of these forming concretions to basically take advantage of all that tasty mineral content that is coming out of it. And they will live on these masses and they will die on these masses. And so you'll have successive generation of these colonies of mollusks settling on top of your concretions, corals, oysters, etc., that are living and dying. And as they die and decompose, they are in themselves releasing calcium ions, which is another very, very important mineral in concretion breaking. Calcium, as we know from our own hard water here in Beaufort, is a very common mineral to find in your water. And this is also contributes to your concretion formation. So we'll often have these very dense calcium layers amongst our iron corrosion based concretion layers inside our concretions as well. So of course, then we have our concretion. So all that has happened and we are left with a concretion. However, as you can tell, a lot of concretions look kind of like rocks. Since concretions are naturally forming geological phenomena, they don't always contain artifacts. So it does pose a bit of a problem and a challenge for archaeologists, when especially at the bottom of the ocean, when they're trying to identify potential artifacts and it's dark and it's murky and visibility is very nil, to try to identify what is a concretion and what just might be a rock. You know, sometimes it's easy. This is obviously a cannon. This one is easy for you. A lot of times, the bigger they are, the more of their own shape they tend to retain. However, most of our concretions are small to mid-sized concretions from the majority of sites, so they look kind of more like these. So a little bit of audience participation, I'm mixing up my words here. Okay, so who here which one is the concretion and which one is the concretion that is just a geological formation that has no artifacts, and which is the artifact containing concretion? So if you think it's the one on the left over here, please raise your hand. Any takers? If you think it's the one on the right over here, please raise your hand. Yeah, and we have a very discerning audience. You are correct. So this concretion over here is an actual concretion that came from the USS Houston, whereas this is just a lovely example of a concretion known as siderite. That's from the Wilkes Formation in Salmon Creek, Lewis County, Washington State. So this is a naturally forming concretion, and this is one that actually came off an archaeological site that probably contains artifacts inside of it. But on average, we don't necessarily know just by looking what's inside of a concretion. So we have to use an analytical method called X-radiography. X-radiography uses X-rays, which are a type of electromagnetic energy, to essentially, and one of the, it's a type of energy that can pass through most things, but not all, as you might know from going to the doctor or the dentist. They kind of put lead on the parts of you they don't want to examine, because lead is not passable by X-rays, but X-rays do a pretty good job of penetrating most types of matter. And what's distinct about it is that it may penetrate the matter, but it doesn't always penetrate different matter to the same extent. And that is important because we can use that to form pictures. So that's how we get X-rays, which you might be familiar with from your doctor's office or your dentist, where we look inside of people to look at teeth and bones and sort of hard tissue. And we use them also to look at artifacts as well. We use these X-rays to be able to penetrate our concretion layer and take a little peek inside to confirm whether or not there are artifacts. So we use and that kind of just kind of go in a little bit more discussion about how X-rays work, is that X-rays are able to penetrate different material to different degrees based on many factors. Sometimes it's the composition of the material that is based on atomic density. So different materials that are composed of different atomic elements have different sort of densities and different abilities to essentially allow X-rays to pass through them. You can kind of think of it as akin to electrical resistance, and that not all materials are able to conduct electricity, and some of them add very high resistance. You have to either increase the power or increase the amount of time you're passing electricity through it in order to complete that current. Similar thing with X-rays is that there are a lot of different factors that go into whether or not an X-ray can penetrate a certain material. One of which is essentially how powerful your energy beam is, so how much energy you're sending through your artifact. That is represented by kilovolts, so potential. Another one is exposure time, so how powerful the beam is, as well as how long you're exposing it to that beam. And then there are other things that are characteristic of the artifact itself, including what the artifact is made of. Different elements with different atomic weights, as I mentioned, will allow X-rays to pass through them to different degrees at different, sometimes at different energies, but generally speaking, as we've seen from lead, it is pretty much impassable in all situations. And other things about the artifact, including like how thick it is, and also the geometry, how complex it is, how big it is, how much space actually has to be traversed by this beam, as well as how many things might be on top of each other, and so we're superimposing each other, all affect the ability of our X-rays to penetrate this material. So it produces a very interesting grayscale image of what's inside of these concretions that could tell us information in various types of information. One of the things it can reveal is, yes, there are artifacts, no, there are artifacts. However, as I've mentioned, since our X-rays can penetrate material to different degrees, and we have to use kind of a high threshold energy just to pierce through this concretion because it is so dense and so thick, to kind of power through that concretion and get that energy beam through, we already have to use pretty high settings, which means there are some materials that show up while others don't. So this is an example of a concretion. You can see the outline of the concretion itself, and you can see it's jam-packed full of artifacts, including metal artifacts from which the X-ray was not able to fully penetrate, so they're actually visible. Whereas you have things that are much fainter, but you can kind of see the shadow of artifacts kind of buried in this concretion. Well, that could be a product of both these just being further back in the concretion and there just not being enough energy by the time the beam sort of got to them at the back of the concretion, or it could be that they're made of another type of material that is not as dense. A lot of times that happens with the organic material inside concretions is that it doesn't tend to show up in our X-rays very well. So a lot of times we have metals that show up quite distinctly, or parts of metals. But we do have to be mindful that when we're eventually breaking these down, there could be organic matter in there, or things made of glass or ceramic that don't necessarily show up very well on our X-rays because they're not as dense as the metals around them, which are much, much clearer, and also just aren't able to kind of withstand the amount of energy we have to force into the concretion in the first place to kind of produce an image. So X-rays can help us confirm an ID, that there are artifacts. This is not just a rock. And they can also help us ID the content in there by giving us a very nice rendering or image of the artifact itself. It can also alert us to different types of materials. As I mentioned, different types of materials which are made of different things essentially will show up differently on our X-rays. They will be relative to each other. So this is all grayscale. So generally speaking, the things that are whiter on your X-ray, and this might look a little bit better, the things that show up whiter and brighter and are less exposed, that tends to indicate something that is relatively more dense, whereas things that are much fainter, we have a lot more of that black background showing through, where there's been a lot more exposure that's happened, a lot more of those X-rays have passed through, tend to be a lot less dense material. So that's one way that we identify lead, for example. It tends to be very, very bright white, whereas things made of iron might have a lot more kind of gradation in them, depending on how well preserved they are in comparison. So, and this is useful to us because it alerts us of things that might be interesting. This is an example of a key that was actually tinned, which means it's an iron key that had a layer of essentially molten tin layered on top of it for decorative purposes, for protective purposes. And tin is a lot denser than iron. You can see right here that its atomic density is a lot higher than that of iron. So it tends to, and lead's even higher. So it tends to show up a lot as these very bright white lines on your X-rays that tells us there's something of very, very unusual dense material that's distinct from the surrounding material around it. And even though iron, like metallic iron, is quite dense itself, its corrosion products are significantly less dense. So that kind of gives us an indication of what might be made of corrosion product, which might versus what might be made of solid metal still. And this is experienced as a grayscale event, as I've mentioned. And this in turn can help us predict preservation states. So it can help us kind of give us an idea of what might be solid versus what might be corrosion product, versus what might be missing. So for an example, these very, very dense white lines that are very well exposed, this is most likely our tinned material here in these little nooks and crevices. In comparison, this much less dense material is probably corrosion product. Since it's a lot less white, it's a lot more exposed. And then we have areas where you can basically just see it's very, very exposed. You can essentially just see the entire black background straight through it. It's pretty much transparent. And these indicate portions where there may not be material anymore. It's either very, very delicate, not very compact corrosion product, or else we might have voids. So we might have missing material, or we might have damage. As you can see here, there's basically a big crack that's running here underneath the corrosion. So that indicates to us that as we're cleaning, we'll know what to remove. We'll know that this area, for instance, is corrosion product. So we'll probably want to remove that to better define the actual shape of the key. Whereas this material is, the key, it's either a mineral form of the key or it's solid metal. And then we'll also be prepared to deal with the voids and the cracks and the damage as we encounter them. And I'll get into that in a little bit more detail later, but essentially we can inject materials that can kind of consolidate or fill in these missing gaps. All right, so what do we do with concretions after we've identified them and studied them a little bit to, basically confirm that they are concretions? Well, first of all, we keep them wet. That's very important because these things have been in water for sometimes hundreds of years. And kind of the rapid change from a wet environment to a dry environment can be very challenging for a lot of artifacts. It can cause a lot of problems, one of which, because it is in a saltwater environment, if we're excavating from the ocean, for example, that salt is actually inside the artifact by this point. You can imagine if you have salts that is inside your artifact and it's okay when it's wet because it's in solution, all of a sudden you're drying it out, that salt precipitates out of solution, it recrystallizes and it's growing. Except it's growing inside your artifact. You can imagine where that might be a problem, where all of a sudden you have the salt growth happening inside your artifact. Or you have something made of metal that, has kind of reached an area of kind of a point of stability in its water environment. You're suddenly bringing it to a new environment where it's all of a sudden it's being bombarded by, oxygen, and all of a sudden the salt is coming out of solution. So you have all this electrolytes. So not only are you kind of a challenge for just sort of the crystalline growth and just things dehydrating and kind of falling apart, you also have renewed corrosion happening as a result, we try to slow this down by often storing them wet and storing them in a slightly alkaline solution, since they are so heavily made of iron corrosion, typically speaking. This alkaline solution kind of acts as a buffer and slows down corrosion for iron-based materials. That's one of the reasons that you might see things labeled as being in like 2.5% sodium carbonate or hydroxide, like in my lab, for instance. And that's basically to try to slow down corrosion and kind of help the transition from one environment to another environment, because it's often that transition point, the very sudden change, which is very damaging to these artifacts, just that abruptness, and also the introduction of new environmental factors and what that kind of precipitates in terms of salt coming out of solution, corrosion happening, et cetera, dehydration, you're losing water. So you might have organics or sometimes even modern materials like rubber or plastics, which all of a sudden are, moisture is being rapidly removed. So that can result in cracking or flaking or basically destruction of your artifact. And this is a rather famous example. This is a cannonball from the Mary Rose. So sometimes the concretions themselves fall apart. We have examples of that if they're misidentified and not placed wet. And you can also have problems even after they're deconcreted, where you have artifacts just essentially kind of falling apart from the inside out. All right, so we store them wet, and now of course we have our guide in the form of X-rays, and we want to break down these artifacts and try to extract them. So how do we do that? So there are both mechanical means and as well as chemical means for doing this. Traditionally, this would have been done using kind of like a hammer and chisel method. Very famously, you'd have people essentially very carefully chiseling away at this concretion, trying to get down to the artifacts. We also traditionally, back in the past, used a lot of electrolysis, which could essentially, one of the byproducts of electrolysis is it produces a lot of hydrogen gas, and that hydrogen gas will build up inside the concretion and basically kind of explode off slight layers. So it kind of pops off layers at a time. So electrolysis used to be used quite frequently in the past as a way to remove concretion from material. Still is to some extent, but we do know that a lot of times that is difficult to control. And also times acid baths were often used to try to digest these materials. However, a lot of these methods were very uncontrolled and the outcomes were very unpredictable and came with a great risk for the artifact. Obviously, chiseling, you can get very good at it. I do know people that are very, very good at it and have a lot of finesse in being able to chisel out artifacts from a concretion. But on average, your average conservator, that's a lot of skill and a lot of precision you need. And sometimes, the cracks, sometimes it's unpredictable what you're going to get in terms like that. So you can actually break your artifact. Electrolysis, you can accidentally sort of explode your artifact from the inside out if you use too high settings. And of course, acid digestion, especially if you have a concretion that has mixed materials in it. So you have organics as well as inorganic materials inside your concretion, then you can get a lot of differential sort of results, and you can accidentally hurt or damage your artifacts as a result. Thankfully, in the last 40 years, we've developed a lot more tools with a lot more finesse. One of the mechanical ways that we now remove artifacts from inside concretion is using these special power tools. They're vibro tools, which basically mean that they use pneumatic air to operate a needle and basically make it vibrate very, very fast. kind of like a miniature jackhammer, and we're able to very quickly and with a lot of precision and control remove concretion, sometimes literally grain by grain in some instances. This technology was actually developed for fossil preparation. A lot of the names of these tools reflect that, like paleo tool, for example. So you can see that you can really get down there to some very fine detail and be very discerning with what you're removing. You can also have a lot of different needle sizes. So you can have very big needles if you're trying to remove a lot of bulk material very quickly. And you can have very, very, very tiny micro needles. So you can move a lot of very, very tiny material, one grain at a time, as I've mentioned. We do still, in some circumstances, use acid digestion as a way to help soften up or remove concretion, particularly with materials like glass that are very fragile, or lead, which is very soft, in which the power tools might damage it in terms of gouging it or breaking it. So in which case we'll kind of but in a very targeted way, we'll introduce a very dilute form of acid, introduce it for a very short period of time in very specific locations to soften up that concretion, in which case we can then go after that area again with hand tools like scalpels and dental picks to then remove the artifact from inside. And to give you an example of what this looks like in action, I'm going to play you a short 2-minute video of some work I've actually been doing back in my lab, in which I've been slowly deconcreting a typewriter from the U-85. So this video will discuss that process a little bit. So please sit back and enjoy for the next 2 minutes. Unfortunately, I don't have any music, so I'll just, and I'm sure you don't want me to actually sing, so I'll just sort of reiterate what's going on. But yes, essentially you'll see a squirt bottle kind of come out quite frequently in this video. And that is because I'm trying to prevent the concretion from drying out so that I don't get things starting to fall apart. I don't want salts coming out of solution. I don't want rust happening. So it's important that I both keep re-wetting this material as well as to try to trap in moisture, which is why you might see these kind of wet rags surrounding it and why only a very small part of the typewriter is currently visible. Yeah, so typically how we try to remove concretion is that we try to remove as much as we can till we get to the point where we get to the surface of the artifact or as close as the surface of the artifact as we can reasonably get. A lot of times, especially in cases where you have voids, where you don't really have much of an artifact anymore, you might have a very thin layer of material that once represented something was much thicker and more intact. A lot of the information detail will actually be, if there's any surface detail like inscriptions or maker's marks, or graffiti, for instance, a lot of that material is actually retained in the sort of most proximal layers of corrosion, so the layers that sit most closely to what would have been the surface of the artifact. They've kind of replaced that surface and keep a lot of that detail. So you have to be kind of careful when you're removing this material that you don't accidentally destroy that detail. You also need to be careful that you don't unintentionally sculpt your artifact. You really have to try to follow what's there to the best of your ability, because it can be very tempting, especially when something is a soft material or very fragile, that you can kind of artificially kind of create the form of what the artifact should be. Yes, and I had to eventually stop the video just because it was the camera was kind of in the way of where I needed to be to get in there. So I had to stop the camera. But this picture that you can see here on the screen is what I basically accomplished within a day of work. So that was almost a full day of work, just deconcreting that one key. And it looks pretty good. You can see the key top. There's a little rim of material surrounding it that's kind of locking in that I'm trying to preserve, et cetera. You can definitely see the difference between the before and the after and how much material I was able to move and just how quickly I was able to do that in. All right, so kind of going back to I keep bringing up the idea that there are voids in our concretions. There's empty spaces where material has been lost. There's damage where things have separated or been broken. So how do we deal with that? So we can also use the concretions themselves as essentially natural molds. We can actually basically insert a casting material into these void spaces, like what you see here with the nails. So usually some sort of epoxy resin. We can essentially inject this into the void space and essentially get facsimiles out. We get a replica of what was there. It acts as a natural mold, which we can then, in some instances, paint or faux out to kind of make them look more realistic. Sometimes there's a very thin skin of the original material still inside the concretion in these void spaces, which the epoxy resin also essentially consolidates and essentially glues to the surface. So we sometimes have essentially a thin skin of material which is being over an epoxy resin core is kind of what happens. And then we have sort of composite artifacts, which have some areas which might be fully epoxy resin or consolidated by epoxy resin. So an example of this key, this would be an instance where we might inject that epoxy resin into the concretion and fill out these missing pieces. So we would basically fill this missing void over here and here, and then consolidate this sort of broken part so we get an intact artifact as a result. All right, so once we've separated the artifacts, what do we do with them? We tend to then basically identify them by the material that they're made out of. We then treat them based on their own needs. So this can be a plethora of different options. Some things don't really need much treatment after they come out of concretion. Getting them out of concretion was sort of the bulk of the treatment that they required, was just removal from that environment. So what we then do is some method of controlled drying. So that means we don't just kind of remove the water. We usually try to have to do it in a slow, controlled method. Sometimes this involves buffered desiccants, which start out as 70% saturated with moisture that we then slowly replace with 50%, 20%, 25%, 15%, et cetera, and slowly decrease the humidity that's surrounding this object and slowly remove the water from around the object. We can also do that in dehumidification chambers, and some materials, especially organic materials, which might have a lot of shrinkage or breakage as a result of losing that moisture, like wood or leather products, for instance, we might actually freeze dry. A lot of materials do get desalinated. As I mentioned, we do have a recurring issue with salts being inside of our artifacts. Either the salt crystals themselves grow inside the artifacts and break them, or else they trigger new corrosion processes, which also results in loss of the artifact very often. So we want to try to remove as much of that salt as possible. So we go through various types of desalination processes to try to pull out as much of that salt. It can be passive, which basically just means it goes through a series of fresh water baths. It can also be more active, where we use a form of electrolysis to help kind of speed up the process as well. We also, for some materials, especially like organic materials, which have a cellular structure like wood or leather, a lot of times the interior of those cellular structures have been essentially eaten away by microbes or eroded away by the burial conditions as a result of being in the burial environment. So what we do is we can't just remove the water, because then the structure will collapse, because essentially the water is what's filling up those cells and bulking them out and keeping them kind of full and somewhat robust. If we just remove the water, then we would essentially have an empty skeleton with all these sort of empty pockets that nothing was supporting it. So it would just collapse in. So we often use go through a bulking process for some things to try to replace the water with a different material that can basically hold the structural integrity of the material. A common one that we use is a material called polyethylene glycol, which is a very common additive to a lot of cosmetics, lubricants, oils, things like that. So it's usually pretty copacetic with most of our organic materials, and it's a good bulking agent. And after this bulking process, materials will then go through controlled drying, usually in a freeze dryer. Some materials, because there is so much iron is very often the seed product, or the byproduct, is what the mineral that which creates these concretions. There's a lot of iron in this concretion, and as a result, there's a lot of iron now inside a lot of the artifacts, even if they weren't themselves made of iron. It's called iron staining. They've migrated into the inside of the artifact, or in some cases, they've actually replaced elements of that artifact. They've mineralized the artifact, so to speak. And that iron can be a problem, because it can keep corroding essentially when exposed to oxygen and air and new electrolytes. And sometimes that corrosion process is very acidic as well. So that can be very damaging, especially to organic materials or things that are kind of fragile, like ceramics, for example. If you have iron staining underneath a glaze layer of a ceramic, you can have basically corrosion happening inside your glaze layer, which often means that you physically lose your glaze layer. Either it's dissolved by acidic attack, or it's physically broken off by the growth of corrosion inside. So we try to remove iron that has migrated onto things that are not iron through a process called chelation, which basically it's a chemical treatment where essentially we introduce a special type of molecule that is designed to bind to metal cations essentially and remove them from the artifacts. And then a lot of things then go through periods of consolidation, coating, and reconstruction, where essentially we might put a protective layer on material to try to buffer it from the environment. Or if we have things that are in pieces like ceramics or glassware, we might try to reconstruct them to a certain degree and try to put them back together using various adhesives and other techniques to kind of reform the artifact. Or it could be any combination of the above. Many artifacts require one or more of these steps at any time. And that is my presentation about concretions and how they form and how conservators deal with them. So thank you very much for listening. And if you like this installment of the Maritime Heritage Series, please do check out the next presentation on May 18th at 11 a.m. by my friend Ben Wonderly. He'll be speaking on the explosion on the steamship Pulaski and the particular wreck, the story of that particular wreck in the Outer Banks. So anyone have any questions? Thank you for listening. No, you do not.
So seashells have a number of minerals.
Yes.
Sand.
Yes.
Could you go over that again? Sorry.
Yeah, so a lot of just like your bones, like your bones are calcium based. So the primary mineral, they're made of different types of minerals, but the kind of dominant one is calcium for the most part. Same thing with the shells on mollusks, for instance. A lot of it's calcium based. And so when those calcium based materials like the seashells start to decompose and start to dissolve essentially in the water, they release calcium cations, so calcium mineral content essentially gets released. And just like with the iron I showed you, that too can then basically form bonds with other dissolved materials that then precipitate out a solution as, solid mineral content, which can then essentially cement other material together like sand, soil, artifacts, etc. And that's, and that is speeded up by things like acid attacks. So like when people talk about the acidification of the ocean, for example, they're talking about how the ocean is becoming a lower pH. So it's basically becoming more acid-like, and acid is very good at dissolving minerals and basically breaking those bonds between them and basically transforming them into, solubilized cations that can then form other things around them. So that does speed up the process a lot.
You didn't speak about bones, but can concretion have no bones?
Yes, I can. Famously, go back to the very beginning. I don't know, can I? Won't. It can, yes. They can form around pretty much anything as long as there is a certain amount of mineral content either around the area or mostly being produced by the artifact itself, because that artifact becomes a nice little nucleus for the formation of these concretions, and more so if that mineral content is being produced by that material. But yes, and try to get back to one of my example pages. Why do I have so many animations?
You have a fossil.
Yes. So for example, too far. All right. So for example, this concretion. So as you can see, there's actually a shell or a piece of a shell here. And this, I don't think is actually fossilized. I think this is actually a shell that is covered in rock form or partially fossilized. It's partially fossilized and partially just gone. So you can see that part of it is actually, there's nothing there. There's essentially a void or an impression of the shell embedded in the concretion. So this material essentially has left the building, so to speak. So it's fully dissolved into solution and gone elsewhere. Whereas this has been fossilized. So this has essentially been, so fossilization is a replacement where you have organic carbon-based material that is replaced by inorganic material over time. There's a mineralization process that happens over a long, long period of time. So this is kind of in between. So you have areas where, the organic parts have fully broken down. The inorganic parts have been dissolved away in some areas, and then other areas they've essentially been replaced by rock, essentially. So that's why you kind of have a weird composite. But yes, you can have, and I don't really have a good, I think I'll go back to that fossilized leaf. But yes, that's still mostly an inorganic. It's kind of much like your bones, it's kind of a mixture of inorganic and organic parts. So there's organic parts to it and inorganic parts, and some of them become fossilized, some of them decompose, some of them dissolve. But then sometimes, yes, you do have purely organic material. Like this obviously was a leaf. So this is a leaf fossil that has become fully mineralized and fossilized over time. So that's why it's been preserved inside of the concretion. Whereas you could also have a situation where you have basically the imprints or a void in the shape of the leaf, where there used to be a leaf that was then concreted over. That leaf, however, was not fossilized. It fully decomposed and went away. So what you're left is basically the impression of that leaf trapped in the concretion. But yes, you can definitely get that with organic material as well. And a lot of times, and it can be protective because that concretion slows down the degradation process of a lot of organic material by blocking off access, especially to decomposers, to microbes that help speed up that process. So it can actually protect a lot of organic material where it otherwise may not survive. So there'll be, for instance, you have wrecks that come from very shallow wreckage sites. Organics often don't survive in very shallow wreck sites because there's too much oxygen, there's too much light, there's too much biological life there. There's too many things that can deteriorate and decompose those materials. But when you get one of these that get trapped inside a concretion, it is protected from the outside environment and can survive sometimes for hundreds of years, trapped inside that concretion. And then maybe, you know, if they were going for thousands and thousands and hundreds and thousands and millions of years, even maybe they'd be fossilized or over time, but or maybe you'd just be left an impression, they would eventually decompose. But, you know, over the course of, 500 years, you can still actually get organic material like cloth sometimes, or, wood, bones, sometimes even, pieces of textile that have survived inside concretion. We've had concretions that have in which paper has survived before because it's been protected by this concreted mass. Does that answer your question, sir?
Can you share with us the element of time that concretion starts?